So, first seminar of the new year. It's a pleasure to have Bob Frame, current member here at the Institute and from the University of Pennsylvania, and he will talk about the 3D kinetic Couette flow via the Boltzmann equation in the diffusive limit.
Thanks, Camilo. I was visiting last semester and already missed visiting and teaching my classes. But I'm happy to come back and be able to talk about my work with my collaborators. This is a joint work with Renjun Duan from CUHK, Chinese University of Hong Kong, and Sengwen Liu from Jinan University in India, who's also from the Chinese University of Hong Kong. When I got my new grant renewed over the summer, my new program officer told me I needed to put the logo on my talks, and so I started doing that. I just put pencil. Okay, so I was asked to give more introduction, and hopefully I succeeded in that. Oh, okay. So this is a picture of Ludwig Boltzmann when he was a young man, and Couette when he was doing an experiment, not quite as young, but they both have years. And these are the academic materials of my talk today, I guess. So show you the layout. Okay, so this is what I want to explain a little bit. So we're studying a class of non-equilibria for the dynamics of the Boltzmann equation. If there's a physical boundary in space, a typical example is the famous Couette flow for the rarefied gas confined by two parallel infinite plates moving relative to each other with opposite velocities in opposite directions. The Couette flow is one of the simplest problems of gas dynamics, but raises many challenging difficulties in its mathematical study. So here's just a picture that I took out of this book by Garza Santos, or you have a planar Couette flow, so you have a plate at the top moving to the right, and you have a plate at the bottom moving to the left, and your flow is happening inside, and you have this function u that's connecting the top and bottom. Okay, so here's the 3D Couette flow. So we're working in a three-dimensional periodic channel domain. So omega is x, and it's x, y, and z, and x and y are the torus, and and you're going between -1 and 1 in the third direction. The torus is periodic. So you have two boundary plates at z equal +1 and -1 moving relative to each other with opposite velocities along the horizontal x direction. And we model that with u plus and u minus, which are plus and minus alpha epsilon in the first component and 0 in the last two components. So alpha denotes the shear strength, and epsilon is the Knudsen number defined as the ratio of the molecular mean free path to represent in a physical length scale. And then we characterize as macroscopic shear velocity for the 3D fluid Couette flow. As u is alpha epsilon z, comma 0, 0 for z between -1 and 1. And u connects the boundary velocities u plus and u minus linearly. So in the previous slide, it's this line that's going between the top and the bottom. Okay, so here's just a picture that I took out of that recent paper in 3D, so I can show you what we're doing, sort of. So there's a plate at the top and the bottom moving in opposite directions. You have a bunch of particles in between, and they're moving around. And we're modeling this situation. Okay, so here is the rescaled. We're studying the Boltzmann equation. Here's the rescaled Boltzmann equation with moving boundary. So the rescaling via the Knudsen number comes in terms of these epsilons. So the epsilon partial t f plus v dot grad x f plus epsilon squared phi grad vf UFF. So Q is non-local, but it's quadratic, so that's why you write it with 2 copies of f in it. And we're going to rescale these epsilons to take the limit from the kinetic equation to the fluid equation. So this Boltzmann equation, the kinetic model is sort of in between particle systems and fluids. Is sometimes called a mesoscopic system. So it's like a intermediate model in between many particle system and the fluids. And when you rescale epsilon and send the Knudsen number to 0, you can derive the equation of fluid dynamics. And so we use the diffuse reflection boundary condition at z equals plus minus 1. So you have a f epsilon and tx and v, and you have either plus minus 1, you have v, and the z component of v can be either positive or negative. And then you sort of average over all the velocities, so you're integrating over v tilde, and you multiply by this Maxwellian distribution at the wall. So here the integration variables are v tilde is vx, vy, z, and f tilde is the density distribution, time t position x and velocity v, and m is the Maxwellian at the wall. So you have this rescaled Maxwellian plus minus that's normalized to have L1 norm equal to 1 and to be evaluated at the walls. And so epsilon is the Knudsen number again, and phi is some external force, and omega is the finite channel domain that we're studying. So this is the model. Oops, I have to-
It's the back.
If you okay, I'll just try to move fast enough so I can keep from sleep. Okay, so here's a picture that I took from Wikipedia just so that I can explain to you that sort of diffuse reflection boundary condition. It's an average over, so you have something hitting, let's say a mirror, and if you had the specular reflection boundary condition, it would just bounce back up in the blue direction. Diffuse reflection mushes everything together and it bounces. It's like an average. It bounces all over. And okay, so this is, I don't know if you've seen this picture before, but I stole it again from somewhere down here. And the idea is with specular reflection, the image of the mountain is reflected very almost perfectly. And with diffuse reflection, the water is choppy and you just get a big mush. So everything is mushed together. And that's what diffuse reflection does. And supposedly the most.
This has to do with the roughness of the boundary then?
I mean, it can have to do with that.
What,
yeah.
what else causes this diffuse reflection?
Yeah, it's basically like if you're talking about light, if you have like a rough boundary and it gets reflected all over the place.
Okay.
And this is just like an average. Instead of doing modeling precisely, you take an average over everything.
So in your problem, you're using this diffusive.
Yeah.
Would the specular reflection be more difficult to do, or?
No, easier.
Okay.
It's a simpler boundary condition.
Okay.
And I'm thinking that if you're like in a tokamak and everything is round, then you're gonna usually use diffuse reflection because you're not flat.
Yeah.
Okay, so I'll tell you about the Boltzmann collision operator. As Q is a function of Q is a function of F1 and F2, and it's also a function of Tx and V. It's a non-local operator in the V variables, in the velocity variables. It's local and everything else. So you integrate over R3 in V star, and you integrate over S2 in the omega variable, and you have this kernel, and then you have F of V prime star times F of V prime minus F of V star times F of V. And so you think of V star and V as the incoming velocities of two particles colliding, and the outgoing velocities are V prime star and V prime. And then the kernel takes this form, V minus V star to the gamma times B cosine theta. Cosine theta is V minus V star over it's a unit vector in the relative velocity direction v minus v star. We assume gamma is between 0 and 1 and cosine theta is that, and you can write it that way as omega and S2 also. So the Boltzmann equation was actually derived by Maxwell, sort of, at least he wrote down the equation in his like big Principia treatise from the mid 18th centuries. And he derived these kernels from a two-body interaction potential. And there's actually a calculation that it's in every statistical, like first year graduate statistical physics textbook today. And he derived these kind of kernels, except without the angular cutoff assumption, but we're using that. This is the grad angular cutoff assumption, v cosine theta less than equal to c cosine theta for c greater than 0. And the reason why the Boltzmann equation, to my understanding, was that actually named after Boltzmann was because he came up with the H theorem, which says entropy is increasing. So should start to slow that down. Okay, I'm just gonna try to slide. Cool. So our assumption covers the case of Maxwell molecules, gamma equals 0, and hard potentials, gamma between 0 and 1, including the hard sphere model, which is the gamma equal 1 and b of cosine theta is cosine of theta exactly. And at the bottom, we have these pre-post collisional velocities, v star and v prime star, and they have this formula. I won't read it to you, but I'll write it again here. So these formulas are a consequence of molecular conservation laws of momentum and energy for elastic collision. So you have this picture of two particles colliding here, and they come in with velocity v, go out with velocity v prime, and they hit each other, but they don't mush or anything. They're hard spheres. And then these velocities are conserved, and from here, this is there are 4 equations here, and there's 6 unknowns, so you get 2 free parameters, and you get these, you can solve for these, what are called pre-post collisional velocities up here. So that's the Boltzmann equation. And now I'm going to talk about the peculiar velocity of gas particles. So you have a velocity v is vx, vy, vz, and the peculiar velocity of gas particles is the velocity relative to the macroscopic shear velocity for the 3D Couette flow. And so you have the macroscopic shear velocity, and then you just define the peculiar velocity relative to be v minus u, and it's v of x minus alpha epsilon z vy comma vz. And so it's the velocity relative to the shear velocity. And okay, so where does this come up? Well, if we take the peculiar velocity, actually, when I first heard this term, I thought it was very peculiar, but it turns out that it's like a definitional term in physics. So the phrase peculiar velocity is like, there's a Wikipedia page for it. And so we study solutions to the Boltzmann equation of the form f tilde is f txv is txv minus u of z. And then we just plug in what u of z is, so you get vx minus alpha epsilon z, vy and vz. And then the Boltzmann equation with the boundary condition is transformed into this equation. So it's the same equation, except you have these extra terms, alpha epsilon z partial xf and alpha epsilon vz partial vxf. And the diffuse boundary condition is pretty similar, except you change from the Maxwellian at the walls to the global Maxwellian, just e to the minus v squared over 2. So Maxwell didn't get shortchanged. You got the main steady state named after him. And then the initial data becomes f epsilon xv is epsilon tilde x v plus u z. So this is the system that we're looking at, and then it has a steady problem. So for the regular Boltzmann equation, the steady states are these mu's, these Maxwellians that are in red down here. But for the this Boltzmann equation evaluated along a peculiar velocity, there's this is the steady problem, and it doesn't have a easily solvable formula for its solution that I know of. So long-time behavior is expected to be governed by solutions to the steady problem that we call FST, with the diffuse reflection boundary condition that you have here, and then you have the total mass set equal to what it would be in the non-steady case. So this is a conservational unsteady case, and you have to enforce it here as a parameter of the problem. Okay, so now I want to tell you a little bit about the linearized equation. So the collision operator for the Boltzmann equation I told you about before is here, and the Maxwellian equilibrium about a few times is mu is e to the minus v squared over 2 times the L1 normalization. And then we linearize as f equals mu plus the square root of mu f. You don't have to do it this way, but this is a convenient way to do it. And then the nonlinear collision operator becomes gamma fg is mu 1 over mu square root q square root of mu f comma square root of mu g. And then the linearized collision operator becomes L of f is minus gamma square root of mu f minus gamma f square root of mu. I could have written it in terms of the q, but it's nicer to look at if you write it in terms of the gamma. And then that's what it is. And you get this, you do this linearization, you get that linearized collision operator again. And the point is that this linearized collision operator has a large null space. So it has a 5-dimensional null space in the v variables. It's a span of 1v, 1/2 v squared minus 3 times mu. But then in the t and x variables, it's 5 variables plus infinite dimensions. So P of L is equal to LP is equal to 0, where P of F is the L2 projection into the null space, and you have rho of F plus V dot U of F plus 1/2 V squared minus 3 times theta of F times the square root of mu. And the coefficients rho F, UF, and theta of F become the fluid variables after the sort of Hilbert expansion that we'll do. So the mass charge density is rho, and the fluid velocity is U, and it's the integral V dot F times square root of mu. And the temperature is theta, and it's 1/6 times the V squared minus 3 times F integrated times the square root of mu integrated over V. And so these are the fluid variables that come up. And they come out of the null space of the linearized collision operator. Okay, so let me tell you about the Hilbert expansion for the steady problem. So Hilbert, in one of his famous Hilbert problems, proposed to connect many particle systems to fluid dynamics and to derive them. And an intermediate step is the Boltzmann equation, and Hilbert actually wrote down this Hilbert expansion. And the idea is that you expand the solution in powers of epsilon, and you plug the expansion into the equation and compare the coefficients of order epsilon. And so if we do this for the steady problem, we get f epsilon st is mu plus epsilon squared root of mu, f1 plus epsilon f2 plus epsilon to the 1/2 fr, and fr is the remainder. You can keep going, but we don't need to. You would just get higher order corrections if you kept expanding. And
why epsilon to the 1/2?
Okay, good question. Instead of going forward, I'll go back. So it's because of this 1/2 epsilon here. So when you plug in the remainder, you get a term that's remainder, and you want to kill this 1/2 epsilon. And so if you have epsilon and you want to be consistent with all the other scalings, And so if you have epsilon to the 1/2 times one FR and epsilon to the 1/2 times another FR, then a whole power of epsilon comes out and it kills the 1 over epsilon.
Okay. But so that term is still larger than the F2 term, which had an epsilon in front. So because you have F1, then you have an epsilon F2, and then you have an epsilon 1/2.
Yes. 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 Okay, so you always go lower, and so you always make the remainder like 1/2 less. So if you go up to power 4, you make the epsilon 1/2 less. And
But it's strange that FR does not appear in your,
it will.
it will.
I didn't write it here on this slide. It will.
Okay.
It's because that, I mean, let me see if I can explain as we keep going. Okay, so you plug the expansion into the steady problem and compare coefficients, and the first coefficient is L, F1 equals 0. And the second one is involves only F1 and F2. So you have L, F2 here, and then everything else is either independent of F or it only depends on F1. And then you have this equation down here, which depends on F2 and F1 and nothing else. And these are sort of separate equations that come up when you do the expansions. So this one comes from the power epsilon. This one comes from the power epsilon squared F2. And the other, and then this one comes from both of these two terms, but it doesn't come from here. And then so the coefficients rho epsilon, rho s, us, and theta s of the leading order F1 satisfy the perturbed incompressible Navier-Stokes-Fourier system around Couette flow. And this is the, so if you so it comes from here. So this is like the fluid equation. And if you let F1 be defined this way, then that's all the solutions to the first equation 9. And then you define F2 by L inverse here, and you get, this is basically L inverse of F1. So F2 is L inverse of F1. And you also have the theta terms that come up that are satisfied by boundary conditions and compatibility conditions. And you can plug in F1 here to everything in this form, and you can calculate all of this F2 in terms of the fluid variables and moments, and then you plug that into this equation, and you get the Couette flow. So this equation, these two fluid equations come out of the third equation right here. And so you choose epsilon to the 1/2 because you don't want it to mix with the F2, and because it gives the good power to control the remainder term. And it can't by canceling 1 over epsilon. So if you chose, so you can't choose epsilon power 1 here. And so you go down and you choose a half. You don't go up.
Then you don't see FR anyway. Then.
I haven't showed it to you yet. Okay, so and this is the remainder for the steady problem. So you have V dot grad X FR, epsilon squared phi, grad V FR is plus alpha epsilon Z partial X FR minus alpha epsilon VZ partial VX FR. And then these are the sort of terms that come from the Couette flow, alpha epsilon VX VZ over 2 FR minus epsilon squared over 2 phi dot V FR over epsilon L FR and epsilon squared gamma FR FR gamma FR F1 plus epsilon of 2 gamma F1 plus epsilon of 2 FR epsilon to the 3/2 F2 minus, and then yeah, you keep going epsilon to 5/2 epsilon to 3/2 minus alpha epsilon to the 3/2 square root 1 over square root of mu V Z partial Vx of square root of mu 2. And okay, so if you want to answer Leslie's question again, you want this power of epsilon here to cancel the 1 over epsilon here that comes out, and you don't want the epsilon in the remainder to be too big, because if you make it bigger than epsilon, then you're going up higher in the expansion, and you don't want to do that. So you make it smaller than epsilon to go lower in the expansion, and then you get this remainder, and 1/2 is kind of the natural choice, so that things stay normalish, and then that the boundary condition for the remainder is this diffuse boundary condition. FR X Y plus minus 1 V, and P gamma is the projection into the diffuse part, but then you also have these extra terms. This is a power epsilon to 1/2, and then there's the projection away from the diffuse boundary, sort of. So this is a remainder boundary condition, kind of boundary extra. Okay. Okay, so for the unsteady problem, when you have time dependence, we do a similar thing, except we expand around the steady state. F epsilon st, so this is the solution to the steady problem. It's not a Maxwellian. But then we put epsilon square root of mu g1 plus epsilon g2 plus epsilon 3/2 gr txv. And now I put the tx and v dependence outside. And now is epsilon to the 3/2, which why do you do that here, not there? And the reason is because there's time dependence. And it changes the scaling. So then you have the initial data as written here for the dynamic problem, and then G1 again will satisfy the will give you the fluid variables, and G2 will be defined by an inverse. But now as a linear operator, but now you have also have F1 showing up from the steady problem when you invert the L operator in G3. And the coefficients for the leading order term G1, rho, U, and theta satisfy the perturbed incompressible Navier-Stokes-Fourier system around the Couette flow. And so this is the Navier-Stokes system around Couette flow. You also have the temperature equation. You have the initial boundary conditions, U times 0 and U at the boundary and theta at the boundary. And so that's the system that you get when you add this velocity. Okay. Yeah, and then the remainder for the unsteady problem is GR, and it's this, again, big monster. I left out some nonlinear terms, but the point is that you have this gamma. This is the main nonlinear term. It's gamma and GR, where that's the remainder, and you have the linear operator over here with a 1 over epsilon L GR, and then you have all these crazy terms over it. And you have the initial data again and then boundary condition again with the boundary condition for the remainder becomes a diffuse part and there's an extra part away from the diffuse part. Okay, so our main goals are twofold. So the first main goal is to rigorously derive the perturbed incompressible Navier-Stokes-Fourier system from the Boltzmann equation. So in a sense, if you prove the existence of solutions and you send epsilon to 0, and you get the and your estimates are uniform in epsilon, then you can say that you have derived a solution to the Navier-Stokes-Fourier system from the Boltzmann equation. And so our second goal is to prove the stability of the dynamic Boltzmann equation around the stationary solution to the steady Boltzmann equation, satisfying the boundary conditions that were on the previous slides. Okay, so to do this, we're going to use the Wiener algebra framework. And so I'm going to sort of explain that to you in a simple way, because I've been doing this with Paco for a while. And actually since we first met, I think, but so for a function f divided by a domain omega, the Wiener algebra is a space of functions such that the Fourier transform f hat L1 of k. So a Tn is f such that the sum over k and Zn of f hat of k is finite. And this is important because it's important to point out that we have the embedding of the Wiener algebra is contained in L infinity. The Wiener algebra is behaves in a lot of ways like L infinity, except it's non-local and it has a little bit more structure. And the space, the Wiener algebra has nice structure because when you take Fourier transforms of products of functions, they turn into convolutions of those Fourier transforms. And when you sum over the convolutions, you can bound that above by the sum over each function individually. And this has no loss. The constant here is 1. And that's why this is nice, because you don't lose anything constant wise. And so when you want to study boundary value problems for the Boltzmann equation, the sort of natural space to work in is L infinity, but for a lot of situations we don't know how to use L infinity. And so this is hopefully helps because this space is almost L infinity. So we hope that we can use the space to do things that we don't know how to do in L infinity, because it has the structure of having regularity. So you have an embedding. So these are two things. So if you want to study a partial differential equation and you want to use regularity, the reason why you want to use regularity is because you want to bound things in some space like L infinity, and you want to use an embedding. And the Wiener algebra has the L infinity embedding, and it also has the nice
which is not the most
product structure. And so that's so you can hopefully use this space without that much loss. Okay, so yeah, so reason it works using the Wiener algebra in PDE. This is not comprehensive. There's a well-known old paper by Duchamp Robert. But actually, one of the first times I talked with Paco, I went to visit him in Diego Cordoba in Spain, and we decided that we were going to use this space we didn't even know what it's called, but we decided we were going to use this space to study the Muscat problem. And so since then, this is not a comprehensive list, but since then, I've done a lot of work using the space in partial differential equations, and it's been a very powerful method that I found for developing sort of low regularity results. And so I won't read you everyone's name, but this is the most recent paper, and I just got finished giving the corrections to the journal 2 years ago. But Okay, so for the kinetic theory, we introduced this function space. So actually I was at a kinetic theory conference at the University of Wisconsin-Madison, and my collaborator Renjan Duan was there, and I was talking about my work on the Muscat problem, and I was talking about the low regularity solutions to the Muscat problem. And Renjan Duan had flown there from Hong Kong to Madison, and he came up to me after the talk and he said, "We should try to use this space for the Boltzmann equation." And that's how this paper, we started doing. But so introduce a function space xt, and we use the torus, and we define the space L1k, L infinity t, L2v, and you take the Fourier transform of f in the x variables, and then you take the L2 norm and the velocity variables, and then you take the sup in time, and outside of that you take the sum in the Wiener algebra. And so these have been called Chemin-Lerner type spaces because the Wiener algebra is outside of the sup in time, so you normally have things in the other order. There's this paper by Chemin-Lerner on Navier-Stokes where they do things in this order, and I presume that's the first paper doing this because everyone named this ordering of the spaces after them. But it's useful to do things that way. Okay. And so we did that. We used that framework, and we were able to it was transcribing, I don't know. Okay. So now in this case of the model I'm studying, we take Fourier transform with respect to variable x is xy in the torus. We don't take the Fourier transform with respect to the variable b. And you have f hat t, k, z, and v, and and you leave z and v alone, and you only integrate in 2 dimensions at x. And so you have k is k of xy, k of x, k of y, and z. And then we use these kind of Chemin-Lerner type velocity spaces. So here now we use L infinity in z and v, and we sum over the modes outside, and we also have the L2 kind of space too, with an L2 wave. Okay, so here's the first distance theorem for steady solutions. So assume L infinity and L2 are greater than 4, gamma is between 0 and 1, and assume a smallness condition on the potential and alpha, where alpha is the shear parameter. And then the steady boundary value problem has a unique strong solution, f epsilon st, and it satisfies that it's when you expand it, it's non-negative, and f1 satisfies it's in the null space of the fluid variables, and rho, u and s satisfy the Navier-Stokes equations as a perturbation around Couette flow, and f2 is given by the good thing from before, and the remainder can be split into FR1 and FR2, where FR1 satisfies this estimate, so it remains uniformly bounded by the size constraint multiplied by a constant, even when you parameterize an epsilon. So, okay, let me not try to explain those norms anymore, but that's the estimate that you get. And okay, and the second main theorem. So if stability of a steady solution, so you assume that the weights are bigger than 4 again, and you assume that initially theta 0 equals 0, and you assume that you have a smallness condition on the remainder, and the eighth derivative of the fluid initial data is bounded, and so these are the derivatives, and these are only derivatives in z. So these are derivatives in different variables, x and y and z. And then you assume your initial data is non-negative. Then the initial boundary value problem has a unique solution, it's also non-negative. And the remainder satisfies this monstrous estimate that I haven't, that I had to put in the tiny font in order to make it fit. But the important thing is here is we get exponential decay. And so the remainder decays to 0 as time goes to infinity exponentially fast. And this, I haven't really explained this at all, but this kind of splitting that we're doing here is due to Russell Caflisch. This is Caflisch splitting. And you split the remainder into GR1 plus square root of mu GR2. And then you estimate each of them separately. And you get good uniform balance on the remainder. Okay, so if you really wanted to see that like horrible equation from inequality for the remainder here, I put it for you here in large font. But let me see. I don't think I have anything else to say about it. Okay, so let me just try to summarize. To the best of our knowledge, these are the first results proving existence and stability of the multidimensional kinetic Couette flow governed by the nonlinear Boltzmann equation with a small Knudsen number. Additionally, in the absence of external forces, our results establish exponential convergence of the 3D time-dependent solutions toward the 1D planar kinetic Couette flow uniformly with respect to small Knudsen number. Yeah, so all the uniform estimates, you can, on the previous slide, you can send epsilon to 0 and derive the fluid equation as a result. Okay, so I want to mention a few previous results. Stability of the Couette flow of the fluid, Bedroisian Moody, short implicit damping, and asymptotic stability of planar shear flows and for 2D Eulers. And in 2015, and then Bedroisian and Germain-Moody studied the stability threshold for 3D Couette flow in 2017. So there's a stability threshold, and then in I think that's ARMA in 2020, Chen, Li, Wei, and Zhang studied the transition length threshold for 2D Couette in a finite channel. And in 2021, Wei and Zhang studied the transition threshold for 3D Couette in a Sobolev space. And so I explained this to Nader Moody not that long ago, and he said, "Oh, you're doing implicit damping," and so I want to clarify to you that we're not doing implicit damping, because so implicit damping uses Gevrey regularity and all this machinery, and so we're getting. So you could like include implicit damping probably in this, but it would be like a next order effect. So we're doing like the first order effect. So if you like, there's this paper, I forget the authors, but it's probably Bedroisian, Moody, Vlad, and I don't know who else, but and they take Navier-Stokes and they include implicit damping for Euler in it, and they get a variety of decay rates. You could probably do that here too, but I wanted to zoom back to what I was saying before and just say you could probably do that here too, but we're just doing the Navier-Stokes part. We're not sort of including the implicit damping of the Couette flow in it. So we don't need that. It would be like a next order effect. Okay, so stability of the Couette flow and the kinetic level in the context of Boltzmann equation has been studied by a lot of authors. James, Noda, and Velasquez studied self-similar profiles for homoenergetic solutions of the Boltzmann equation in 2019. And then in the collision-dominated case, they studied the large time asymptotics. And then they also studied the large time asymptotics in the hyperbolic dominated case. And Bogolev, Noda, and Velasquez in 2020 studied self-similar asymptotics from Maxwell Boltzmann equation. Then Ranjan Dwan and Liu studied the Boltzmann equation for a uniform shear flow, and Liu and Yang studied the Boltzmann equation for the planar Couette flow in 2021. And Dwan and Liu studied the uniform shear flow for the Boltzmann equation with hard potentials. And Caflisch studied long-time behavior of homoenergetic solutions in the collision-dominated regime for hard potentials, and many other works. Okay, and there's also many other works linking fluid and kinetic Couette flow. So Coron studied the derivation of slip boundary conditions for the Navier-Stokes equation from the Boltzmann equation in '89. Esposito, Leibowitz, and Mara studied hydrodynamic limit of the stationary Boltzmann equation in a slab in 1994. Esposito, Leibowitz, and Mara studied the Navier-Stokes limit of stationary solutions of the nonlinear Boltzmann equation in '95. Esposito, Guo, Kim, and Mara studied stationary solutions of the Boltzmann equation and the hydrodynamic limit in 2018. And there's a Duan, Li, Yang, and Zhang studied the heat transfer problem for the Boltzmann equation in a channel with a diffuse boundary condition in 2022. And sort of the moral is that the relative motion at the boundary gives you the Couette flow with the peculiar velocity. Okay, so some ideas in the proof. We use the Fourier transform on T2, and that allows us to reduce the 3D problem to 1D. And we use these anisotropic Chemin-Lerner type spaces and the Wiener algebra, and they allow us to bound the nonlinear terms and to control the singularity associated with small Knudsen number and the diffusive limit. And we use the Caflisch decomposition that I told you about earlier, combined with the L2 L infinity technique. That helps us to manage the growth of large velocities. So the L2 L infinity technique was developed by a lot of different authors, in particular Yang Guo, someone whose name I think of when I think of the L2 L infinity technique. He's worked a lot on boundary plot problems for the Boltzmann equation. And yeah, so since I tried to give more introduction, I'm not gonna sort of punish you by making you hear about the proof anymore. And thank you. So this is the first result that I told you about earlier with this crew. Global model solutions that laying out a non-credible Boltzmann equation from 2020. And in that paper, I think for perturbed solutions, we got the lowest, even today, the lowest regularity solutions for the non-cutoff and Landau equation. And my goal was not just to sort of flex muscles and try to go as low as regularity and as I could. My goal was really to study boundary value problems and to study boundary value problems you need to use low regularity. And so now we are doing that some more with the 3D kinetic Couette flow and the diffuse limit. And this is the paper I told you about today, the second one. So thank you.
Questions? So here's one thing that I've not understood. So if you let epsilon go to 0,
Yeah.
do you derive in a new way the existence of the solutions to the fluid equations?
Yeah, right. So yes. So that's the Hilbert. That's a yes. I mean, so the way we're doing this, we're proving existence of solutions. So there's two ways to do this. One is to take these solutions and do a Hilbert expansion. Suppose you have a theory of existence for these equations. Take that off the shelf and plug it into this expansion, and then get estimates for all the remainder terms, and then say you build a solution to the Boltzmann equation from a solution to the Couette law. But we're proving the existence of solutions to the Boltzmann equation and stability, and then deriving from that in the small epsilon limit the Navier-Stokes-Fourier system. So you're so you're getting a deriving in a, so I wouldn't say it's a new way, because the Hilbert expansion has been around for a long time, but it is a different way. And for this model, it's new.
Because you have enough compactness to send
Yeah,
things to zero.
yes.
Okay. Okay. There are no other questions. Thank you.
Thank you.